Hello, and welcome to another episode of the Math Club podcast. This is episode 3, Thinking Outside the Box. My name is Pete Littig. I am a software engineer and former math professor, and I have a lifelong love of mathematics.
And my name is Noah King. I'm an elementary school teacher who's been teaching for over 25 years, and I also love math.
So Noah, I've been going through my email inbox, and I need to get back to you on an email. You wrote me back in April of 2010, I think.
Oh, finally.
Yeah,
I've been wondering why I haven't been hearing back from you.
Sorry, it's taken a day. But you were writing to me about a really neat math problem related to a predictor.
I remember. Yeah. Are you talking about Newcomb's paradox?
Yes, that's the one. Why don't you tell everybody what that problem's about?
Okay, yeah, sure. Newcomb's paradox. This is a fun and tasty thought problem that has some pretty interesting mathematical implications. The problem was introduced by William Newcomb, but he's not the one that actually made it famous. Back in 1969, a philosopher named Robert Nozick wrote a paper about this problem, and this is how Nozick presented the problem in that paper. So let's pretend, Pete, that you are a contestant on a game show. And my question for you is, how would you like to win $1 million?
$1 million?
$1 million.
Yes, that's right, Dr. Evil. Well, here is the situation, and here's what you would have to do to win the money. So you are on the stage, and in front of you, there are two boxes. We're going to call them Box A and Box B. Okay. Box A is transparent, and you can see that there is $1,000 sitting right there in that box.
Sure. Okay. Sounds good.
Box B is opaque. You can't see what's in it. You have a choice. You can either choose to take only Box B, whatever's in it, or you can choose to take both boxes, A and B. The host of the show tells you that they have a reliable predictor. That is, somebody who has made a prediction about what you are going to choose today when you're on the show. If the predictor predicted that you are going to take only Box B, then they have placed $1 million in Box B, yours for the taking as long as you choose to only take that box.
Okay, so you're saying right now there could be $1 million in that box, Box B.
That's right.
Okay.
However, here's the catch. If the predictor predicted that you were going to take both boxes, then they have put nothing in Box B.
So $0.
$0. So the question is this, Pete. What do? You have the choice right now to either take just Box B and whatever it contains, or to take both boxes A and B and whatever they contain. But you do know that this predictor has never been wrong before. They've done this many, many times. And every single contestant who has come on the show and picked just Box B has walked off with
$1 million.
Every contestant who has chosen both boxes has found Box B to be empty and has walked off with just $1,000. So what do you do?
Okay, well, I would rather have $1 million than just 1,000. I think my family would agree with me that that would be the best outcome. Can I ask you a couple of questions? So when you say reliable predictor, okay, what is this predictor? I mean, is it a person? Is it a computer program? Do I need to worry about that?
I've seen different variations of this paradox written up, and that part's not really important. Sometimes it's a supercomputer. Sometimes it's an alien. Sometimes it's just some kind of supernatural being with this ability to make reliable predictions. I don't think that part really matters. What does matter is that you know this predictor has never been wrong in the past.
Has never made a mistake. Well, so what you're saying right now is leading me to think that a reasonable choice would be to take Box B and leave. I mean, sounds like everybody else who did that got $1 million, but maybe there's $0 in that box. And then choosing just that box would mean walking home empty-handed. Well, here's what I'm thinking. Standing here, looking at these two boxes, either the money has already been put in the box or it hasn't. But you're telling me that that's all been taken care of before I even showed up, that the boxes were set in place. Is that right?
Yes.
Well, if the money is already either there because it's going to be there, or it's not there because the predictor decided not to put it there, why don't I take both boxes? This way, if the money is there, I walk away with $1,001,000. And if the money isn't there, well, then at least I get $1,000. And that's not a bad consolation prize. So I kind of think maybe I'm going to take both boxes.
Well, that is certainly one way to look at it. I would take box B only. And let me tell you why. If this predictor is perfect in their skills to predict, if I know for a fact that this predictor has accurately predicted what I'm going to do, then that's the same thing as saying, I know there's $1 million in box B. And if I know there's $1 million in box B, I'm going to take just box B and get that $1 million, because I also know if I take both boxes, that million isn't going to be in box B because this perfect predictor would have left it out. So I'm going to disagree with you. I'm going to say it makes more sense to choose box B only.
All right. All right. Now, you know I don't pay a lot of attention to you when we have these conversations, but I'm pretty sure you didn't say the word perfect until just now. So what do you mean by perfect predictor? Because if what you're telling me, if what you're saying is this game just amounts to, hey, Pete, would you like $1 million or would you like $1,000? Well, that's not much of a game, and I would take the $1 million and say, thanks a lot.
Okay,
but
that's a very good point. And to be fair, the problem, as Newcomb originally stated, it did not say this was a perfect predictor. It said that this was a reliable predictor. By saying the predictor's never been wrong, I guess I'm extrapolating that means he won't be wrong this time either. But just because he's never been wrong before doesn't mean he won't be wrong now.
Yeah, I see. So I think we can introduce the language of probability here to help us. When people talk about real-world events like flipping a coin or weather patterns, they make predictions based on empirically observed outcomes, things that happened in the past and can be used for calculating probabilities about future events. So what I think you're saying here is, if we set up a typical probability fraction, in the numerator, the number of times the thing has happened, and in the denominator, the total number of times that the trial was conducted. So for example, the denominator here would be the number of times the predictor has made a prediction.
Okay, well, just for the sake of having real numbers, let's say before you appeared on the show that 100 contestants have appeared on the show before you. So the denominator will be 100. The numerator will also be 100 because I'm telling you that the predictor has predicted accurately every single time. So 100 100ths of the time.
Right. Now, it needs to be understood that that is not a theoretical probability. That is an empirical probability. It's entirely possible that something which has happened 100 out of 100 times might not happen the next time the experiment is run, in which case the new probability estimate would be 100 over 101, which would be slightly less than 1, right? So I think if I'm understanding your idea about perfect predictor, that would be the situation in which the universe is so constructed that that fraction will never dip below 1. It will always be 1. It has always been 1, and it will never change.
Right.
And that makes this problem a little bit, well, then it just boils down to, hey, Noah, do you want $1 million or not?
So just to make sure that I'm understanding, we agree then that if the predictor were a quote-unquote perfect predictor, there's really no difficulty in making this decision. You would just take box B.
I think that's right. But let me say one caveat. We do not live in a universe where that's the way things work. We have theoretical models that are derived from mathematical formulas that generate theoretical probabilities. But in the real world, things don't always work out, and they certainly don't work out always and forever under any possible scenario. So I think, yeah, I might say, sure, I would take just box B, but it feels a little bit like now I'm no longer playing this game. I'm playing the, hey, Pete, do you just want $1 million game? And in that game, I would say yes.
Let's add something to make it a bit more realistic then. Let's go back to Nozick's initial formulation of the problem and say it's not a perfect predictor, it's a reliable predictor, and all that you know is that this predictor has never been wrong in the past.
Right. Yes, I think that's still pretty compelling. In that situation, even with a predictor who has never made a mistake, I still want to say, look, the money is either in box B or not. It's already been put there. I would be somewhat foolish to walk away without choosing both boxes. I don't want to go home empty-handed. If the predictor does make a mistake, I go home completely empty-handed. And since the money is already there or not, it's sort of like, does it matter what I do?
Well, Pete, it turns out that you and I are illustrating two different but equally reasonable approaches that Nozick talks about in his paper.
My approach is more reasonable than yours. Yeah, though there are two approaches that are widely considered by scholars who study what's called decision theory. Nozick himself was a student of decision theory. The first approach is based on a quantity known as expected utility. I'll get into the details of that in a moment. The second approach is called the dominance principle. And that principle really finds its home in this kind of game theoretic setting. Game theory not meaning, hey, we're on a game show, come on down, you're the next contestant, but more a strategic interaction where people's decisions may impact each other.
Okay, and I did see while skimming Nozick's paper that he mentioned both of these principles, but maybe you could explain what they are and make it a little more clear.
Sure. You are a proponent of the expected utility approach.
For example, when I turn on a light switch in my living room, I expect the utility to come on.
You really need to just listen here because that's not what I'm talking about. So,
okay, sorry.
Okay. Well, here's the expected utility principle. Given the choice between several different options, you should choose the option that maximizes your expected utility.
Okay, and so for the predictor game, the different options are choosing only box B or choosing both boxes?
Yeah, right.
Okay, then let's start with taking both boxes. How would we find the expected utility of that choice?
Well, we start with an assumption. We assume that the predictor is correct with probability P, where P is some real number between 0 and 1.
You know, maybe we should remind listeners a little bit about probability before we get too much further here.
Oh, sure. Okay. We can think of probabilities in terms of percentages. If a predictor is correct with probability, say, P equals 0.75, then we'd say they're correct 75% of the time. So if this predictor makes predictions for 20 games, we can figure out how many times they'd be right by multiplying the probability P with the number of games played. In this case, we'd get 20 times 0.75, or 15 times.
Yeah, that makes sense.
Also notice that being right and being wrong are mutually exclusive outcomes. So if the probability of the predictors being right is 75%, that means the probability of them being wrong is 25%.
Right.
Okay, great. So, Noah, if you take both boxes and the predictor has correctly predicted this, what's the outcome?
I would get $1,000.
Right. And that's what we'd call the value or the utility of this outcome. You get $1,000. But this outcome isn't guaranteed, right? There's a probability involved. Since the predictor is correct with probability P, we can multiply the probability and the utility together to get something I would call a probabilistic utility score. And in this case, we would get 1000P.
So if the predictor is correct 75% of the time, then we get 1000 times 0.75 equals 750.
Yeah.
So, but what does that even mean? There's not a way for me to win $750.
That's true. You can't play a single game and win $750. But if you play the game many times and keep track of your winnings, you could end up winning on average $750 per game. Now, in order to complete our calculation of the expected utility, though, we need to consider what happens when the predictor is wrong.
Okay, because we have to consider all options when we're considering the expected utility of a choice.
Exactly. All of the outcomes are important. So what would you win if the predictor was wrong then?
Well, in that case, I would get $1,001,000, right? Because the predictor would have incorrectly put $1 million in box B, And I'd also get the $1,000 from box A.
Yeah, that's right. And the probabilistic or weighted, let's say weighted, it's easier to say, the weighted utility here is 1 minus P, which would be 0.25 in this case, times $1,001,000. That gives $250,250. And if we add these weighted utilities together, we get the full expected utility of taking both boxes, which is $251,250.
Okay. And again, this is just showing me my average expected winnings if I played multiple times and always took both boxes.
That's right. That's one feature of this type of expected utility calculation is its real calculational value is in the long run. It may or may not be accurate on any one playing of the game.
So in a game like this one where you're only playing it once, this approach isn't going to be as helpful as it might be in other scenarios.
Well, it certainly can be helpful, but the numbers that you calculate, they have probabilities attached to them. You can't treat it as, oh, this is guaranteeing me $750 or $250,000. That's an indication of some probabilistic outcome that really only takes place over time.
Cool. So if I have this right, then the expected utility becomes smaller as P becomes larger, right? But that would mean that for a more and more reliable predictor, this is a pretty bad strategy. If the predictor's perfect and P equals 1, then I can expect to only win $1,000 if I take both boxes.
That's right. This does seem to suggest maybe you don't want to take both boxes.
Okay. Well, let me try calculating the expected utility of the other choice, of choosing just box B, just to see if I understand. All right. So if the predictor's correct, then I'd get $1 million. So the weighted utility in that case is 1 million P. And if the predictor's wrong, well, then box B is empty. So I think the weighted utility would be 0, right?
Yeah, $0 times 1 minus P, but that's still $0.
Right. Yes. So that means adding those together, the total expected utility for choosing box B would be 1 million times 0.75 or 750,000. Well, now that's almost 3 times higher than the expected utility we got for choosing both boxes.
You got it. And we now have 2 expressions, each of which depends on how likely the predictor is to be correct.
And I feel like what you're describing here is an exact argument for just taking box B, because what you're saying in essence is if I take both boxes, I only get the million if the predictor was wrong. And the predictor has shown in 100 out of 100 trials that he's never been wrong.
Exactly. And that is why you favor this approach of calculating expected utility, because it resonates deeply with you at a very intuitive level. You see the logic and you are compelled by it.
That's right. So what's the other principle?
The other principle is called the dominance principle, and it goes like this. If you were allowed to make a choice from some number of options, if one of those choices always produces a better outcome for you, then you should choose that option. I mean, it makes sense, right? If you know that one choice will be inferior, guaranteed to some other choice, then you should make the other choice.
Well, in this situation, is there a choice that will always be a better choice?
Yes. So the day I show up to play the game, I can see the $1,000 in box A. I have no idea what's in box B, but money has already been placed there or it hasn't been placed there. So now, if I choose just box B and I find that there's $1 million there, wouldn't it have been better had I taken both boxes? Because in that case, I would have the million that I just described and the $1,000 from box A.
Yeah, but why risk that? That's the part that I don't understand about this approach. Why risk it? You're essentially risking the whole...
$1 million.
Don't you think we should maybe ask for more than $1 million?
I see what you're saying. So do you agree that when I show up at the game on the morning of the filming, that the money will have been either put in the box or not? It's already there or it's not there. Do you agree with that?
Yes.
Okay.
Yes, I do.
Okay, so now let's suppose that the money is not there and I choose box B. I'm going to go home empty-handed. So in that case, it would have been better for me to take both boxes because then I would go home with at least $1,000. On the other hand, if the $1 million is in box B and I just choose box B, I go home with $1 million. But again, if I choose both boxes, I will go home with $1,001,000. So in both cases, it is a better outcome for me if I choose both boxes. So that choice dominates the choice of choosing box B. And to me, wanting to play rationally, that's clearly the better option.
I get what you're saying, but I would also say, I think it's the expected utilitist in me that would say,
is that a word?
It is now. It's the expected utilitist in me that would say, when you take both boxes, you are banking on the fact that the predictor was wrong. If the predictor was right, then there will not be the $1 million there in box B. So your dominance principle only helps you if that predictor made the wrong prediction.
Yes, I understand what you're saying, but let me put it to you another way. Suppose that box B, which I cannot see into, is open on the back, and my spouse or my partner or my friend, whoever I've brought with me, is sitting on the other side of the table and can see what's in box B. They have complete and perfect information. The rules don't allow that person to communicate with me, but let's just walk through the scenarios in terms of what they might be thinking. So if box B is empty, what would they be wishing me to do?
They would be wishing that you take both boxes.
Exactly. Because, hey, at least so we can go home with $1,000, right? And if box B has the $1 million in it, what would my partner be asking me to choose in that case?
I guess in that case, they would also be hoping you take both boxes.
Again, it's both boxes. So I don't need to have an open-backed box and a partner on the other side of the table, because I know if there were a person sitting there, that's what they would tell me in both cases. Take both boxes. And this predictor, who even knows? This seems a little sci-fi to me. I'm going to be honest. The predictor seems a little sci-fi to me. And I think what my approach does is it grounds everything in rationality. And it says, take both boxes.
What's actually really funny to me about this, Pete, is how strongly you feel about the correctness of the dominance principle and how strongly I feel about the correctness of the expected utility principle.
Yeah.
In fact, if you go back and look at Nozick's original paper, there was a quote that exactly touches on this. He said, to almost everyone, it is perfectly clear and obvious what should be done. The difficulty is that these people seem to divide almost evenly on the problem, with large numbers thinking that the opposing half is just being silly.
I really do think you're silly.
And I think you're silly.
Right. It may surprise you to know, I also have looked at Nozick's paper. He does happen to be a two-boxer, just like me. So I feel like I'm in pretty good company. But along those lines, halfway through the paper, Nozick says, so listen, I'm going to advise you, put this paper down. I want you to come back to it, but put it down for a few days and just thrash about with this problem, because that's exactly what he did, this thrashing about. And I understand why he feels that way. It's really tough to somehow end the cycle of, well, but you have a point. Oh, but you have a point too. But maybe I should consider just taking, you know?
You have a point.
Thank you. Thank you. I think so. I think it's very interesting to recognize that many bright folks who have looked at this problem before the two of us also find that, yeah, it's slippery. And I think that is one of the coolest things about this problem is its slipperiness, that we're not going to find an obvious answer. And that's a little unusual for many people when it comes to something that feels mathematical in nature, right?
Well, but it makes sense when you consider that this paper wasn't written by a mathematician. It was written by a philosopher.
Well, okay, granted, but lots of mathematicians have taken a look at this paper and this problem. In fact, when I was teaching at the university, I taught a course on game theory, and we used a really excellent book for the class, a book written by Philip Straffen called Game Theory and Strategy. One of the chapters is a game theoretic study of Newcomb's paradox, and in that chapter, the author does take a mathematical approach. one way that we might try to get ourselves out of this split view that we have is to push on some of the parameters a little bit. So here's a question for you, because I know how convinced you are that you should take box B. So let me ask you, what if in the clear box, box A, you could see, let's say $100,000? So the choice now becomes, do you want $100,000? If you pick both boxes, you will get $100,000 from box A and whatever happens to be in box B. I know you think there's nothing in box B. So therefore, you'd be going home with $100,000. Guaranteed. That seems pretty good to me. And if the predictor happens to make the wrong prediction, you would also go home with an additional $1 million. Would that be enough to tempt you into taking both boxes?
Well, it's definitely more tempting when there's more money in the clear box that I know for a fact I will get.
Yeah.
I'm not sure where the break-even point would be on that. How much would have to be visible in the clear box for me to give up the expected utility?
So when does the expected utility of taking both boxes equal the expected utility of taking only box B? You will probably be delighted to find out that the probability cutoff is 50.05%, which means the predictor only has to be slightly better than a coin flip for this calculation to tell you take just box B. And again, I'm sort of making your argument for you that the expected utility approach does suggest that even if the predictor is barely better than a coin flip, you should still take just box B. As an interesting follow-up question, something that you and other listeners could consider is, well, what if instead of a predictor, just a coin flip was used? Like, that's how the game works. They start with a coin, they flip it. If it comes up heads, they put money in the box. If it comes up tails, they don't put money in the box. And now you as a player on this game have to decide what to do in that situation.
Well, that's different because now I don't feel like whether or not the $1 million is in that box is dependent on my decision. In the case of the predictor, I actually do feel like it's dependent on my decision, that the normal cause preceding effect has been upended and flipped around so that now effect is preceding cause, that the cause is my decision and the effect is how much money was put in the box. They just happen to happen out of order.
Right. Yes. Right. Which, by the way, is how I know that if suddenly a DeLorean pulls up in front of your house and Doc says, "Get in, Noah, we're going for a ride," you're going to get in because you're going because you are open to this idea of like, hey, time got reversed. Sweet. Let's go find Michael J. Fox.
Right.
You know?
So just to make sure, after all this discussion, what we're saying is that this problem has, for decades, led many, many people to come to opposite conclusions, and that we are an example of the two different conclusions that a player might come to when playing this game. If I were standing there on the game show, I still happen to think that in that moment, I would choose to just take box B. And I guess what you're saying is, in that moment, you would choose to take both boxes.
I wish that it were that easy for me. It's actually a little bit harder. So here's my big reveal. I've been thinking about this a lot. Do you remember, you read the play or saw the movie Rosencrantz and Guildenstern Are Dead?
Yes. I think you're probably thinking of the opening scene.
I am, right, where the coin flip comes up heads 92 times or something like that.
Heads.
So I thought to myself, all right,
Heads.
if I had a coin that was told to me to be fair, and I started flipping it, and it was heads.
Heads.
Some ludicrous number of times in a row. But I had absolute assurance from the universe itself that this coin is fair.
Heads.
And I had to predict, there was $1 million on the line, what the 100th flip would be.
Heads.
99 times it's come up heads. I have to predict what flip 100 will be. I thought, well, I know what I would do in that setting. I would say, I don't care that my mathematical model would suggest that this next flip could be either heads or tails with equal probability. I am going to throw that out the window.
A weaker man might be moved to re-examine his faith. If in nothing else, at least in the law of probability.
Heads.
I'm going to go with my gut instinct, and I'm going to say heads. I would put all my money on heads. And in this particular problem, I'm going to do the same thing. This is not a cop-out, by the way. I want to make that very clear.
So wait a minute. So you would take just box B?
I would take just box B.
Well, then in that case, welcome to the Millionaires Club.
I knew you were going to say that. All right, but just for our listeners, let me say one thing. Rationally, I do think the correct analysis here is to use the dominance principle and to take both boxes. It's just too tempting, right? Either the money is there or it's not there. That's just a compelling empirical fact. However, I know myself, and I am an intuitive, often go with your gut kind of person. And if I were on that stage, I know in the last minute I would take just box B because my intuition would override my reason. And so begrudgingly, regrettably even, I'm going to choose just box B.
All right. And then after the show's over and you have your $1 million, do you want to go get some burritos?
Yeah. If I have $1 million, I'll tell you what, the burritos are on me.
Great. Because I'm pretty hungry already. So we would love to hear what all of you listeners think you'd choose. We have created a Google form where you can share your choice and tell us any thinking that went into choosing the way you did. That form can be found at bit.ly/mathclubpodcast-EP3 for episode 3. And we'll also put that link into our show notes.
And of course, we always love to hear from you with any feedback or topic suggestions for future episodes. You can find us in 2 different places.
Our Twitter handle is @MathClubPodcast, and our Gmail address, mathclubpodcast@gmail.com.
All right. Thanks for the conversation, Pete, and we'll see you next time.
See you next time. Bye-bye.